analytics and reports. Download the app now. Ultimate route to JEE success with JEE Test Prep app by Extramarks. Adaptive testing platform. India's top faculty. Micro-scheduling. Live and recorded sessions. Doubt-solving sessions. National level weekly test. Analytics and reports. Download the app now. Ultimate route to JEE success with JEE Test Prep app by Extramarks. Adaptive testing platform. India's top faculty. Micro-scheduling. Live and recorded sessions. Doubt-solving sessions. National level weekly test. Analytics and reports.
स्टार्ट करो. Hello students, a very good evening to all of you. My name is Ankush Kaul and today I'll be taking a session on a very important topic of JEE, that is simple harmonic motion. Every year we see 3 to 4 questions coming in JEE exams, whether it is mains or advanced, from this particular chapter. This chapter as a whole is basically a combination of concepts which have been picked from different chapters throughout your course of JEE. Maybe it is physics 11th class, kinematics, maybe work power energy, and alternating current from 12th class, waves from 11th class, wave optics from 12th class. So all these chapters like waves, wave optics, electromagnetic waves, then we have alternating current, SHM, sound waves, light waves, these all are interrelated and interconnected to a very deeper extent. So today I will take you through what all basics we need to understand to realize the complex conceptual. So students, concentrate, a very interesting chapter, and I'll take you through some animations, diagrams, questions and a mix of everything. So let's start. Simple harmonic motion. To understand this motion, we need to understand two types of basic motions. One is called as periodic motion, another is called as oscillatory motion. So once we know what periodic motion and oscillatory motion means, then it will be very easier for us to understand what a simple harmonic motion is actually made up of. So to start with, I'll first define this periodic motion. You have already studied kinematics in 11th class and know that there is a particle which goes around in a circle, and because it is uniform, so this particle is going to go with a constant speed v, and say it is going around this circle in anti-clockwise direction. If radius of the circle is r, speed is v, and say this particle starts at point A, how much time will it take? Uniform circular motion, the speed will remain constant. So this is total time taken to cover one circumference or come back to point. Whether it is its first circle to go back to A, whether it is its second circle, third revolution, fourth revolution, nth revolution, any revolution is going to take these many seconds to complete. So that means this particle comes back to point A after a fixed interval of time. This is called as periodicity, and such kind of motion is called as a periodic motion, where the particle comes back to a particular position after a fixed interval of time. Not just physics, in real life. For example, today is my lecture. It was scheduled at 8:45 p.m. So every day if I come at 8:45 p.m. for all the regular students, this system will become a periodic system, because every day you will see me at 8:45 p.m. So periodicity is something which we need to understand, that when something repeats itself after a regular interval of time. So for example, in this uniform circular motion, what we see is repetition after a regular interval. This is for what? Beta periodic motion. We have second definition here, or second type of motion. Second type of motion which we call as what? Oscillatory motion. Now oscillatory motion, the best example of oscillatory motion is to and fro motion. Any to and fro motion can be considered as an oscillatory motion. So to and fro we know, for example, if I take you through these lists of motions, the first one, revolution of the moon around the sun. It is a circular motion, so I will consider, after every fixed interval of time, moon comes back to a particular point. So it is periodic motion. But is it oscillatory? No. Why it is not oscillatory? Because this motion is not to and fro. It is not a back and forth motion, right? Second is motion of a pendulum in a clock. Motion of a pendulum in a clock. We know we have clocks which are pendulums. If you know the time period of those pendulums is 2 seconds. In 2 seconds, the pendulum of that clock completes one cycle or one oscillation. So pendulum of a clock shows periodic motion as well as it shows us oscillatory motion. Motion of the swing which is shown. So in this slide, if you see, we have 3 different examples. I will take you through each one example. For example, first this vertical spring mass system. If you look at this system, the mass which is attached to this spring, the mass is confined to move within this boundary, correct? So within these two red lines, the mass is moving and it is oscillating about a fixed axis. If I bisect this entire region by this dotted line, this fixed axis is basically which bisects the entire length over which the mass is moving. And if I choose any point, say this one, point P, you can see that this mass comes back to point P after a fixed interval of time. So one, it is a back and forth motion, it is a to and fro motion, so it is oscillating. Second, the mass is coming back to point P or any such similar point in this entire space. After a regular end, after going once down and once up, it comes back to P. Every time it comes back to P in a fixed interval of time. So this kind of motion is periodic as well as it is what beta? Oscillatory. Similarly, if you look at this swing, these two girls are having fun here on this swing. And if I draw a vertical line which bisects this swing, so this vertical line here bisects the space over which they are oscillating or they are going to and fro. And if I mark this blue point, you can see the girl with white hair is coming back to this blue point after a fixed interval of time. Once she goes forward, once she comes backward, she hits this blue point. Or even the girl with the black hair. So this type of motion is also what? It is periodic as well as it is to and fro, so it is also oscillatory motion as well as periodic motion. Third is this pendulum, which we know is similar to this swing. Again, you can see a back and forth motion and also you can see periodicity. But in these three systems, we are assuming certain things. And what are these assumptions which we need to take into consideration? These assumptions are, number one, because we are defining two types of motion, one is periodic, another is oscillatory. So I will also define certain assumptions along with these two types of motion. The first assumption is, wherever we see or in this discussion, wherever I am showing you any diagram or animation, I am saying that there is no energy loss. No energy loss is happening anywhere. If energy loss is not there, such kind of oscillations are called as undamped oscillations. Undamped oscillation in JEE mains, they will ask you one question on damping. Sorry, in JEE advanced, not in JEE mains. One question will be on damping, where we have exponential terms that we will see later in the course. But as of now, we are only dealing with undamped oscillation. So there are 2 points along with this assumption which we need to take care of. These 2 points are, which I am going to write here. So first point is, which clearly will differentiate between periodic and oscillatory motion. All periodic motions, are they oscillatory? Can you look at this uniform circular motion? Is it periodic? Yes. But is it oscillatory motion? No. So all periodic motions does not imply that the motions are also going to be oscillatory in nature. So all periodic motions cannot be oscillatory. Fine. This is very important point. Second point, the vice versa. All oscillatory motions can be periodic, can be periodic when that assumption holds. What is that assumption? That energy loss, I will write delta E loss, energy loss is equal to how much, beta? Zero. So if there are undamped oscillations, they can be considered as periodic. So are all periodic motions oscillatory? No. Example, uniform circular motion. Are all oscillatory motions periodic? No. Why? Because if there are energy losses, the periodicity is not going to maintain itself in the system. So this initial thing should be clear with all of you. And these are some diagrams. So if you look at these three systems now, they are periodic as well as they are what, beta? Oscillatory in nature. Such systems which are periodic as well as oscillatory in nature, such systems which are periodic as well as oscillatory in nature, such systems show a particular type of motion, and that particular type of motion is called as SHM. So in our cases which we have discussed, if we have periodicity as well as we have oscillatory behavior, so we will say that the motion is what kind of a motion? Simple harmonic motion. But these are not the only two things which we need to take care of. There are certain other properties also which we will learn in this lecture itself, that when can we call a particular motion a simple harmonic motion. So before taking deep, now let us come back to oscillation. Say we have a particle along this horizontal plane to and fro, and at some instant t its position is x from the origin, and it may be moving forward, it may be moving backward. As of now we are not going into that. So there is a mathematical expression which explains all the types of oscillatory motions which we are discussing here, and that expression is F is equal to minus k into x raised to the power n. F is equal to minus kx raised to the power n. Nothing to be afraid about this equation. We will learn each and every aspect of this equation in due course. So what this equation means, first thing, what are the constraints for this equation? The constraints are that the value of n should always be an odd number. This is the first thing that you have to keep in mind. And now let us put one odd number value of n. Say I put value of n equal to 1. And then I see for different values of x, what do I get as f? So if I put x equal to 0, f is 0, right? If beta x is negative, f becomes what? Positive. If beta x is positive, f becomes what? Negative. Correct? Even if you put n equal to 3, n equal to 5, n equal to 7, you are going to get a similar table. A similar table with these three aspects. That is when x is 0, f is 0. So the first aspect, that is when x is 0, f is 0. This is the position where the net force on the particle is 0. And we call this position as the position, or we name it as the mean position. What we call it? Mean position. A position in this discussion where the net force on the particle becomes how much? 0. Then we also see that if x is in forward direction, the force will be in backward direction. If x is positive, f has to be negative. Or if x is in backward direction, that is x is negative, force has to be in forward direction. F is positive. Clear? So this is definition of SHM. There must be a point, a mean position at which net force becomes 0. Then at every other point, the direction of displacement and force should be opposite to each other. Should be opposite to each other, or we can say position rather than calling the word displacement. The position, if x is positive, f has to be negative. If x is negative, f has to be what, beta? Positive. We'll learn about this in further discussion, but as of now what we have understood, oscillation system ka equation is what? F is equal to minus kx raised to the power n, and we keep the value of n as any odd number. We get these three conditions, this one, and this one, and this is how we define a particle under oscillation. Fine. Now in this case, f is equal to minus kx raised to the power n. This is our equation for what? Any system which is under oscillation. And if I do slight modification in this equation, what is that slight modification? That slight modification is, I will put value of n equal to 1, which I have done previously also, but unknowingly. This time I am doing it knowingly. N equal to 1. When I put n equal to 1, this equation gets converted into f is equal to minus kx, or I will say the value of force becomes proportional to negative of displacement. This equation f equal to minus kx with a special characteristic, that is oscillatory equation may put n equal to 1. This is the equation of a simple harmonic motion. F equal to what? Minus kx. Now whatever the particle is, say this is particle P. It is moving in this direction or it is moving in this direction. This is the mean position, say x equal to 0. This is the mean position where force is also equal to 0. So this particle is moving at any time t. At this point it is at time t seconds and the position is x meters from the origin. So this particle will show SHM if it satisfies this equation. What is that equation? F equal to what, beta? Minus kx. And if we look at it further, this particle may have some mass, say m kgs. Then this equation gets further converted into, instead of force, Newton's second law, mass into acceleration is equal to minus kx. Correct? Or I can write the acceleration of the particle is equal to minus k by m into x. And we know what is acceleration. Acceleration is a double differentiation of displacement or position. So d2x by dt square will be equal to minus k by m into x. The most important equation in SHM. And what kind of equation is this? Sir, this is a second order double derivative, correct? Differential equation. Okay. Do we have a solution to this equation? Yes, sir, we have a solution to this equation. We can find the solution to this equation, but as of now, we will confine ourselves to what is the basic equation of SHM. What is the basic force equation of SHM? It is F equal to minus kx. What is the relation between acceleration and displacement, or acceleration and position? Acceleration is minus k by m into x, or I will write it as acceleration is proportional to minus x. If this happens, then the particle is under what kind of motion? Simple harmonic motion. The term simple in this simple harmonic motion, the term simple has been derived simply because of the ease of calculations that we are going to do. Okay, there can be n number of harmonic motions. There can be complex to complex mathematical calculations involved in harmonic motion, but the term simple does not have any hidden meaning. It just means that the mathematical calculations are going to be very easy for you. So in this discussion, what we have seen, this is our mean position. Fine. This is, say, one of the extremes. I will call it as one of the extremes plus a. This is the symmetrical extreme on the other side. I'll call it as minus a. And any particle P having mass m, if it is released from this position, it is what? released. Why I am using the word release? I just take this particle from my pocket and place it at this point M. At point M, what is the value of x? Beta, this is positive direction, this is negative direction. At point M, value of x is positive, so plus x. So force should be negative or positive. So at point M, force has to be negative. So force on this particle will be in this direction. So the moment I take out this particle from my pocket and place it at point M, this particle is going to start its motion and it is going to start move towards the mean position. And it will start moving towards the mean position, and this will be the direction of its velocity. Clear? So I'm just touching one particular position of this particle while it is under SHM, and what happens when I just release the particle at that particular position. And it follows the expression what x is positive, f is negative. So f is inversely proportional to what, beta? Minus x. I hope the basic equation is clear. The double derivative equation, the second order differential equation is clear, and the basic equation of SHM is clear, and also it is clear what happens to a particular particle when we release it. Fine, along the axis on which it has a tendency to oscillate or a tendency to show simple harmonic motion. And what we mean by tendency to show simple harmonic motion, let us proceed to next slide and I will tell you. So tendency to show simple harmonic motion is the particle must fulfill certain conditions, and only then the particle is going to undergo this simple harmonic motion. What are these particular conditions? Let us take these conditions one by one. The first condition is there must be a stable equilibrium position. Work energy power chapter mein you people have in great detail understood what a stable equilibrium position means. For example, if this is a hemispherical bowl, I have a particle here, same particle, say point P. We like this particle a lot, and I apply certain push on this particle. When I apply certain push on this particle is going to go slightly above and then come back and perform certain oscillations. Minded my discussion is only confined to energy loss is equal to how much, beta? 0. Fine. So when this happens, what we say is this particle is going to undergo oscillations about this vertical axis, or I can call this position, this vertical axis, as the mean position. Unlike a case where I have a particle placed on the same hemispherical upside down, and when I apply this force on this particle, the particle goes to the seventh heaven and never returns back. So before we disturbed whether particle A or before I disturbed particle B, both the particles were in a state of equilibrium. Net force on both the particles was 0. But the moment I disturb particle A, it starts oscillating, and finally when oscillations, if they stop, if there are energy losses and oscillations stop and die down and damp, the particle A will come back to the same position finally. Which means it is very difficult for us to change the equilibrium state of particle A, or it is very difficult for us to divert or deviate particle A from its equilibrium position. Unlike the case of particle B, slight hit and B is gone, and it never returns back. It does not even bother to come back to its original position. But before I projected this particle, or before I had hit this particle with any force whatsoever, small or big in magnitude, the particle A and B both were at rest and in equilibrium state. So these both particles were in a state of equilibrium, but there is a difference in the two types of equilibrium that these two particles were possessing. Particle A was possessing a special type of equilibrium which was called as stable equilibrium, and particle B was under a different altogether type of equilibrium which is called as unstable equilibrium. Any particle, any body for which it is easy for us to disrupt its equilibrium. Easy to disrupt its equilibrium. It is unstable equilibrium. Any particle for which it becomes very difficult for us to disrupt its equilibrium, right? So that is almost in which equilibrium state? Stable equilibrium state. In this universe, every particle, every human being, every object tries to come to a stable equilibrium state. Always, they always tend to go towards stability. So same is the case here also. So if oscillations happen in particle A, and if there are no energy losses, the oscillations will continue till in time infinity. And if there are energy losses, these oscillations will die down eventually, and the particle will come back to point A. So oscillation or SHM, what we will study, only happens about a fixed point, and that point must be what beta? Stable equilibrium point. And in our discussion, sometimes we have also called this stable equilibrium point by a different name, and the name is very familiar to you, and we call it as what? Mean position. So we say the particle is oscillating about the mean position. The particle is showing SHM about the mean position. Basically, the particle is showing SHM about its stable equilibrium position. So this is one condition of an SHM, that there must be a stable equilibrium position about which the particle will show SHM. Second is symmetry of the limits of oscillation about this stable equilibrium position. What do we mean by limits of oscillation? Limits of oscillation means the amplitude. What beta? Amplitude. We have seen in previous slide, I will take you back, that the maximum value of x on this side is plus a, the maximum value of x on this side is minus a. So these oscillations are confined within minus a to plus a. And plus a, or say this position is small a, this position is small b. Small a is as much distant from mean position or stable equilibrium position as the point small b. So the limits, that is plus a and minus a, these limits of oscillation about stable equilibrium position must be symmetrical about this stable equilibrium position. This is the second condition for SHM to happen. What is the third condition? Third condition is something which we have already done, but I did not reveal the name. So that is Hooke's law. Hooke's law says, Hooke's law says F is equal to minus kx. This equation is derived from Hooke's law. So that we already know. If this equation is followed, then it is an SHM mathematically. Next point is change in velocity must always be smooth. Very important point. You see, pendulum, what happens in a pendulum? In a pendulum, there is extreme position, say plus a, mean position 0, negative extreme minus a, and so on. Correct? In this pendulum, if you see, where is kinetic energy maximum? At mean position, we know kinetic energy is what? Maximum. So at mean position, we know velocity is what? Maximum. At extreme position, we know velocity is 0. The pendulum comes to rest at extreme position. At this extreme also, we know velocity is 0 because pendulum comes to rest at this extreme position. Or in potential energy terms, we can say at mean position, potential energy is minimum because the pendulum is closest to the ground. At plus a, potential energy is maximum because the bob of the pendulum is highest from the ground. Similarly, at minus a, potential energy is maximum. So where potential energy is maximum, kinetic energy is minimum, and vice versa. We know this from our previous knowledge. So change in velocity must always be smooth. What do we mean by change in velocity must be smooth? If you see from O to A, velocity is increasing. From A to O, velocity is, from O to A, velocity is decreasing, correct? From A to O, velocity is increasing. From O to minus A, velocity is again decreasing. From minus A to O, velocity is again beta what? Increasing. Whatever is changing in this velocity, increase or decrease, this change has to be very smooth. This change cannot be abrupt or sudden, because an abrupt change in velocity means an abrupt change in kinetic energy. An abrupt change in kinetic energy means you have given some extra energy to the system all of a sudden. And when you supply some extra amount of energy to any already oscillating system, which is, happily oscillating, and you suddenly give it some 10 joules or 100 joules of energy all of a sudden, the meaning of all the oscillations which were there or the meaning of the SHM which it was happily undergoing gets, dissolved. Correct? So then we say that it no longer exists in an SHM till it again comes back to a happy moment with some new amplitude or with some new frequency with this new energy. So there must be no abrupt change in velocity, or I will say mathematically, if I have to say something, let's use some mathematical terms also. This velocity must be a continuous function. This velocity must be what, beta? A continuous function. There must be no discontinuity in this velocity. Last point, amplitude of oscillation is not a function of frequency. Amplitude of oscillation is not a function of frequency. What it means? Let's see. So, it means simply, say there is a pattern, mathematical sinusoidal pattern, and its amplitude is A and its beta frequency is F. Fine. I supply some energy to this mathematical function or to a system which is being represented by this graph. So when I give some energy, say 10 joules of energy, now the pendulum is going to go to a larger extreme position. That means the amplitude is now going to increase. So when I give it more energy, it will now oscillate with a bigger amplitude. And say that bigger amplitude is A dash. But you know what? Though amplitude has increased from A to A dash, but this does not mean that the frequency will also change. Fine. So if you give some energy to an SHM, it will increase its amplitude. Fine. And if amplitude increases, it does not imply that frequency must change. It does not imply frequency must change. Though in some harmonic motions, I'm not saying simple harmonic motions, in some harmonic motions which are not in our course, in our syllabus, which you will study when you enter IITs and all, which are called as non-linear harmonic motions. In non-linear harmonic motions, amplitude is a function of frequency. But as of now, when we stick to our course, that is simple harmonic motion, amplitude is independent of the frequency, right? So these are 5 conditions which I have taken you through for an SHM to occur. I hope the 5 conditions are clear with all of you. Let's proceed. Next. Now, few definitions with those SHMs. The first definition, very familiar thing, frequency. What is frequency? Sir, it is reciprocal of time period. What is time period? We have already discussed. If it is a periodic function, time take minimum time or shortest time taken to come back to a particular point. If we meet after every 1 hour, so our time period is 1 hour. You see me after every 1 hour, after every say 10 seconds, so our time period becomes 10 seconds. Fine. So in this case, frequency is what? Inverse of time period. But what does it mean? Theoretically, what frequency means, right? So frequency का unit will tell you more about what it means is, frequency का unit is beta 1 hertz. Okay. And hertz, the name comes from him, the scientist. And hertz means oscillation per second. Oscillations per second. For example, if we go back to that uniform circular motion wala concept, right, this diagram. So this particle is continuously going around in this circle, right? Say he covers this circle in 2 seconds. Fine. So his time period is how much? 2 seconds. Fine. In how much time he will cover 2 cycles? 4 seconds. In how much time he will cover 3 cycles? 6 seconds, and so on. What is the frequency? Frequency is 1 by time period. 1 by time period bole to what we will say? 1 by 2 hertz, or what beta? Half cycle per second. What do you mean by half cycle per second? 2 seconds for one cycle, 2 seconds for one cycle. So how many cycles in 1 second? Sir, half cycle in 1 second. Correct? So how many revolutions, how many cycles, how many times do we meet in 1 second? Say we meet after every 20 nanoseconds, correct? Say we are very fast. We are fast enough. And we meet after every 20 nanoseconds. So can you find frequency? How many times we meet in 1 second? Right? How many times we meet in 1 second? How many revolutions a body covers in 1 second? How many cycles they cover in 1 second? How many oscillations take place in 1 second? This is how we define what beta frequency. So let's go back to our discussion. And then there is another term related with frequency which we call as what? Angular frequency. This angular frequency is, if I tell you, for the same uniform circular motion of radius how much beta r, particle is moving with a constant speed v, going in anti-clockwise direction. Time period, if I write, I will write 2 pi r by v, correct? Now what is angular frequency? How much angle is covered per unit time. Frequency is what? How many cycles are covered per unit time. Angular frequency, how much angle is covered per unit time, or how much angle is covered in one cycle, not per unit time. How much angle is covered in per cycle. So what I will write? Theta, angle covered per cycle. So theta, in one cycle it covers how much angle beta? 2 pi, that is 360 degree, 2 pi radians. And in one cycle, in how much time? How much time it takes to cover one cycle is time period. Fine. So angular frequency will be given for this uniform circular motion as what? 2 pi by 2. Now there is a very important point. In rotational motion or in circular motion, we often learn about another omega, correct? And that omega is called as angular velocity. This omega is called as angular frequency. This angular velocity is to be used with rotation concepts, circle concepts, but angular frequency is to be used with SHM oscillation concepts. So whenever we are dealing with waves, oscillations and all, we will mostly use the term angular frequency rather than saying angular velocity. And when we are doing, rotation and circular motion, we will use the term angular velocity, not angular frequency as much frequently. Right? So this is a point which you have to note down. So this is all the theory. Now let's see some example of a periodic SHM. I have a function here, f of t equal to a sine omega t or f of t equal to a cos omega t. You know what is the graph of sine or cos? Beta, this is the graph of sine. And what is the graph of cos? Sir, this is the graph of cos. Correct? Here a, small a is amplitude of the oscillation. So beta, this will be small a, and also for this one, this will be small a. Or maximum displacement from the mean position, that we know. Omega t is called as argument of the function. Fine. Omega t ka dimension will be what? What will be dimension of omega t? Angular frequency into time. This will have dimension same as dimension of angle. So this omega t angle is called as what? Argument of this function. Now we have to see, we know this is a periodic function, correct? Sin theta is a periodic function, cos theta is a periodic function, we know this. Can you find what is the time period? So I can directly go to the graph, and graph tells me that this is one cycle, and then same cycle repeats itself, and then another cycle repeats itself, and then so on. Correct? So after how much time the cycle repeats itself is called as time period, but after how much angle it repeats itself. So that I clearly know this is beta 180, so this is 360 degree, so this is how much? 2 pi radians. So 2 pi is the angle after which the sine function or a sine omega t repeats itself. Similarly for cos also, if you look, this much portion gets repeated again. Right? So here also if you look at this point, this will be how much? 2 pi radians. So what is the time period? Time period of this particular wave is what? Time is what? Angle covered by angular frequency. Correct? How did I get this equation? Go to previous slide. See, what is angular frequency? Angle by cycle period, correct? So 2 pi by t, so t is what beta? 2 pi by, or angle by omega. The angle which it covers in one cycle is how much? 2 pi. So it is a periodic function and whose period is equal to how much? 2 pi by omega, not 2 pi. 2 pi is the angle after which the cycle repeats itself. 2 pi by omega is the time period. So this is one thing that you have to keep in mind. Is that clear? Fine, we have covered lot many things, but very basic things. Let us further see what all we can understand from this SHM. Here I have a particle and there are certain conditions which are given to us for this particle. At t equal to 0, the particle starts its motion from, so this is the point where the particle starts its motion, or say I release the particle from this position. Where will this particle go? X is positive or negative? X is, see, look at this table, from plus A to O. From plus A to O, so in this region, X is positive. Correct, beta? Achha, tell me, when it goes from plus A to O, why it goes from plus A to O? Because force will be directed in which direction? Towards the mean position. Correct? Force is always towards which position? Mean position. X is positive or negative? X is equal to plus A, so X is positive. Now as it goes towards mean position, X is increasing or decreasing? Sir, X is decreasing. Correct? It is coming closer and closer to origin because of the influence of this force. If X is decreasing, we know that F is proportional to minus X. So F is also decreasing. If F force is decreasing, means acceleration is decreasing, Newton's second law. Correct? Velocity, because this is the mean position, at mean position velocity has to be maximum, and this is the position where I released it, so velocity here has to be 0. So what is happening to velocity from plus A to O? Velocity is what, beta? Increasing. Correct? Then from O to minus A, now when it reaches mean position, it has gained some velocity. Will it stop here? No. Inertia will come into play and the particle will start moving further away from the mean position in this direction. Fine. So when it further goes in this direction, force is always in which direction? Force is always towards mean position. Now when it is going from O to minus A, value of X is negative, left side of the origin, and X is now increasing because the particle is going away from the origin. If X increases, F increases, Hooke's law, acceleration increases, Newton's second law. At extreme position, velocity is 0. At mean position, velocity is maximum, so velocity has decreased. Correct? Similarly, we can fill rest of the table when it goes back from minus A to O. Back from minus A to O. So now value of X is still negative and now it is coming closer to origin, so X is decreasing, so F is decreasing, so A is decreasing. Velocity at extreme is 0, velocity at mean position is maximum, so velocity ka value has increased. From O to plus A, now X becomes positive, correct? From O to minus A, X is negative. Now X becomes positive, and it is going from O to A. Fine. It is going from O to A, so X ka value will now increase. Force will also increase, acceleration will also increase. What happens to velocity? It goes from mean to extreme, so velocity should decrease. So this is what happens to these 4 parameters while a particle is under SHM on this horizontal axis, say, and same things apply to, a pendulum or a spring mass system or certain other systems which are under simple harmonic motion. Is this clear? Right? Next. This diagram here simply shows you how the particle is oscillating at t equal to 0. The particle is at x equal to plus a. At t equal to t by 2, it reaches minus a. Fine. Then at t equal to t, it comes back to what, beta? Plus a. I'm not going into t equal to t by 4, t equal to 3t by 4, which is a detail. But you need to think about one thing: the lengths of the arrows attached to the particle indicate the speed of that particle. So you can see, where is the length of the arrow maximum? The length of the arrow is maximum at the mean position. There are intermediate speed values for those positions between O2 minus a and O2 plus a. And there is no arrowhead attached to this circle or this circle or this circle, because the velocity at extreme positions is how much? 0. Students often ask a question, sir, if velocity at extreme is 0, why does it go back? Fine. So for that, go back to previous slide. Say at this position, velocity is 0, but there is a force which is pulling it towards, what, beta? Mean position. Correct? And because this is the position where value of x is maximum and f is directly proportional, so if x is maximum, it implies f should also be what? Maximum. So extreme position is the position where the value of force on the particle is maximum. So this force tends or entices this particle to come back to its mean position. That is why the particle is still moving even after its velocity becomes equal to how much? 0 at extreme position, because of the influence of the maximum value of force at extreme position. Right? So till now we have learned lot many things. I hope you were with me and you were understanding. Just the last thing, which is more of analytics: velocity and acceleration of this particle as a function of position. For acceleration, though we already know, acceleration is equal to, we have already written, minus omega square into x. Okay, that means this is a linear equation because power of x is 1. So if you look at this graph, which is a graph between acceleration and position, it should have a negative slope, correct? And the value of this slope must be minus omega square. So if this angle is theta, how much is tan theta? Tan theta must be equal to what, beta? Minus omega square. So this is one graph or relation between a and x, that is a and x are linearly related to each other, but there is a negative sign which gives us a negative slope to the straight line, right? There is another graph which we can see, and to understand that graph, I will write the same equation, this one, in a different form. I'll write it as v dv by dx is equal to minus omega square into x. We know from kinematics acceleration can be written as v dv by dx, or I'll write v dv is equal to minus omega square x into dx. Students, what do I need to do next? We have dv and function of v in numerator on one side. We have dx and function of x on in numerator on other side. So my next step, my intuition tells me it has to be integration. So when I integrate both sides, what do we get? Integration v dv is equal to minus omega square constants out integration of what? X into dx. Correct? Now this particle is basically, this is mean position. Say at any instant t it has a value x, and at this instant its velocity is v. Correct? So at any random value of x, because I have to give limits to this integration. Limits means just choose two boundary conditions within which you are integrating this expression. So I'll keep one lower limit as variable x, and for this x the value of velocity at this position is v, and upper limit I know if I say plus a, at plus a extreme position, velocity ka value is how much beta? 0. So I'll simply say when x becomes plus a, the value of velocity becomes how much? 0. Is it clear? Limits. Limits means choose any two boundary conditions between which you can integrate the expression and get a final result. So if I look at this integration, v dv is equal to minus omega square integration x dx limits x to 0, sorry, limits x to a, and here my limits are v to 0. So when I integrate this, I get v square by 2 is equal to omega square into a square minus x square by 2. Correct? Correct? Very simple integration. 2 and 2 go. So we are left with v is equal to omega root of a square minus x square. Or I can rearrange this expression. I will call it equation 1, but I will rearrange. I don't like this. I'll bring a very, a very happy form of this equation. Let's see what it is. I bring omega this side, I bring root this side, so this becomes, I bring a square this side, so this becomes v square by omega a ka whole square plus x square by a square, and this is equal to 1. Now some of you might have understood why I said this looks a more proper equation, because this is nothing but equation of the form of this y square by y max ka square plus x square by x max ka square is equal to 1. And if you remember, beta, this is equation of an ellipse. Fine. This is equation of what? Ellipse. Very important. So if you compare these two, what is the maximum value of velocity? Sir, it is omega into a. What is the maximum value of x? That too we already know, it is the amplitude, and in this equation also you can see it is how much? A. Correct? Okay, understood. Go back. When we go back, we look at this graph. I'm only showing half of the ellipse here, not the lower part. And you can see on y-axis we have velocity, and on x-axis I have the position. The maximum value of position is a, and the maximum value of velocity is what, beta? Omega a. So this is an ellipse graph. So velocity and acceleration both are a function of position. Acceleration is a linear function of position, and velocity is an elliptical function of position or the graph between velocity and position is what? Linear. You need to remember both the equations, but not a very complex thing which I feel here. So v by omega a ka whole square plus x by a ka whole square should be equal to 1, what, beta? 1. And this is the proper equation of an ellipse, and I have shown you the graph also. So this is how we derive relation between what and what. So we have done till now acceleration versus position, and also we have derived a relation between velocity and position. Correct? And then in the later course we will also derive other derivations like acceleration and time, velocity and time, position and time, and so on, and we will dig deeper into this analysis, right? Fine. So let's take some examples, some questions. The first question is sin omega t plus cos omega t. This is example of a function, and we have to say whether it is periodic or whether it is not. Fine. We know sin omega t is periodic, we know cos omega t is periodic, but is the summation of these two also periodic? So for that, what I do is I'll do a simple thing. I will multiply and divide by root 2. Fine. So 1 root 2 of numerator I will write as it is. The denominator wala root 2, which I know is also sin 45 and is also cos 45, 1 by root 2. So how I will write it in this equation is, I'll write this as sine 45 sine omega t plus cos 45 cos omega t. Is it correct? Fine. So is it sine A sine B plus cos A cos B? So it is root 2 times sine of A plus B. What is A? Omega t, and B is how much, beta? 45 degrees. If I call this as y, so y becomes what? Root 2 times sine of omega t plus pi by 4. Fine. And because it is a single sine, hence it is periodic. So summation of sine and cos. But one thing to be kept in mind, this expression as well as this expression, what is the frequency? This also has a frequency of omega, and this also has a frequency of how much, beta? Omega. So one, to there is superposition of the two trigonometric functions, but also their frequencies are same. So if their frequencies are same, we can directly say that the superposition of these two waves will also be an SH. Clear? This is one of the example. Second example, exponential function ae raised to the power minus omega t. We know that graph of an, we need not do any calculations this time. Say this expression is equal to y. So this is beta y and this is t time e raised to the power minus omega t. We know what kind of function is this, sir. This is an exponential decay function. And the graph of this exponential decay function is something like this. And it continues to go like this, and it runs or it touches x-axis somewhere at infinity, which we also call as asymptotic behavior at infinity. It almost runs parallel to x-axis at infinity. And you can see the values of y are continuously decreasing. There is no periodicity, nothing is coming back. There is no to and fro behavior, there is no periodicity. So this expression is not a periodic expression. Fine. Another example, log x. Do you know what is graph of log x? Y is equal to log x. Sir, log x ka graph is something like this. Okay. So what I can see is, again, the value is continuously increasing. So is it periodic? No, because there is a single unidirectional trend. There is no to and fro, there is no back and forth, there is no periodicity which I can see. So log x is also not a periodic function. Fine. These are few examples to see whether a function is periodic or whether a function is not periodic. Right? Now there is a question. A particle executing simple harmonic motion with amplitude A has maximum velocity V0. So say this is the graph V versus X, and this maximum velocity is how much, beta? V0. At what displacement its velocity will be V0 by 2? So we need to find displacement, correct? Let me change color of the pen, right? Let's make it red. So what displacement its velocity will be V0 by 2. So displacement and velocity, do you have any expression between displacement and velocity? Yes sir, we know ellipse is there. But before ellipse also we had derived one expression. What was that expression? Equation 1. V equal to omega into a square minus root of a square minus x square. So if I look at this expression, I will write V is equal to omega root of a square minus x square. At what displacement its velocity is V0 by 2? So if I put velocity as V0 by 2 is equal to omega root of a square minus x square. Fine. And if we do our calculations, we will get at what displacement the value of x will be equal to almost root 3 by 2 times A, which is, if I convert it into decimals, 0.866 times amplitude, or or I will write it down here, particle has covered 86.6% of its displacement towards amplitude. So on this graph, say this is the value V naught by 2. Where do you achieve this value V naught by 2? Sir, I achieve it at these two positions. What are these two positions? Sir, these two positions are, this is minus A, this is plus A. Okay, fine. So what is this? Sir, this is 0.86 times A plus, and this is minus 0.86 A. Clear? Second part, what is the velocity at displacement A by 2? Reverse case. Now when displacement is A by 2, what is the velocity? So again I will write the expression V is equal to omega under root of A square minus x square. Now what is the velocity when under root of A square, instead of x we have to write what beta? A by 2, when the displacement is half. Correct? Again you will find that time velocity is root 3 by 2 times V naught, the maximum velocity. Obviously we have done some substitutions, which we know maximum velocity is equal to A omega, which we know from our previous discussion. So in this graph, where do you represent those points? So this is again V, this is x, this point will be plus A, this point will be minus A. Now he is telling us when the displacement is half. So beta, this A plus A by 2, and this will be what? Minus A by 2. So this point is what? Plus A by 2, and this point is what? Minus A by 2. So what is the velocity corresponding to these 2 points? The velocity corresponding to these 2 points is what? 86.6% of maximum velocity. Is it clear? Fine. So this is how we are going to solve some basic questions on SHM. We have done two types of problems. One, how to find whether a function is periodic or not, and second is where we are supposed to use the function of velocity as a function of position from the mean or from the stable equilibrium point. And also we have understood this ellipse, which is very important for JEE problems. So students, thank you very much for listening, and I hope this was a useful session for you and for all JEE aspirants. And towards the end, I would like to request all the students to see there is an app link given in the video, and this is the JEE app where you will have access to huge repository of such kind of video lectures and huge repository of question papers and questions and mock tests and previous year papers, national level weekly tests. Please go and download this app and see how much useful it will be for an JEE aspirant once you use it. And do practice the questions, do practice the mock papers as much as you can. More you practice, more fluent you will become in your final examination. So with this message, I end up my today's session. See you soon. Thank you so much.